Great, okay. Thank you very much. And thank you all for organizing the symposium and for your interdisciplinary hospitality in inviting me. It's an honor to be able to participate in these discussions and in the celebration of Akshay Venkatesh's achievements. So, as an anthropologist, I'm quite used to being the most clueless person in the room, at least initially. But I am not so used to talking with scientists and mathematicians who show as much open-minded interest in learning about anthropological, sociological, and historical studies of their own fields, as you have done. I have learned a lot in the past days, and I'm grateful for your generosity and patience with my queries. So today I'll try to address the topic of the symposium from a perspective oriented by the history, sociology, and anthropology of science and mathematics. In doing so, I'll engage with some of the questions raised by Akshay's insightful essay on the potential impact of automation on future mathematical research. And I want to begin with the question of proof. So one of the recurring questions during the symposium has been what counts as a mathematical proof? So I want to approach this question historically. So how have our standards of proof changed over time? But I will not try to be historically comprehensive. Okay? Instead, I will focus on selected major shifts that I find especially relevant for the questions we've been considering at the symposium. And I will begin by focusing on one major fork in the history of proof, which in my view expresses a lot of the tensions that have emerged in our discussions over the past days. I want to call attention to a distinction between two competing ideals of proof. So borrowing the terminology from philosopher Ian Hacking, we might call them the Cartesian and the Leibnizian ideals of proof. Now Hacking uses them in the lower case because he's using them as a kind of ideal types, right? Not necessarily as the most accurate representations of the views of René Descartes and Gottfried Leibniz. But still, these names allude to views associated with Descartes and Leibniz in the 17th century. So in the Cartesian ideal of proof, in Hacking's wording, after some reflection and study, one totally understands the proof and can get it in one's mind all at once. In the Leibnizian ideal of proof, every step is meticulously laid out and can be checked line by line in a mechanical way. So these ideals are very difficult to achieve, in these formulations in practice, right? And neither ideal has been achieved completely, much less required, in most actually existing mathematics. And this point resonates a lot with Andrew Granville's talk from yesterday. So mathematics has always involved a mix of the two ideals, or more precisely, a mix of various standards that we may see as derivative forms of both ideals. And in the history of mathematics since the 17th century, there's a lot of back and forth between different groups defending different versions of ideals that emphasize understanding and ideals that emphasize mechanical checking. Right? To give an accurate and nuanced account would actually require a much longer discussion. But if I were to try to venture a rough generalization, I might say something like the following: that over time, the Cartesian ideal of proof has developed into less strict practical standards, and let's call them, just for convenience, post-Cartesian standards of proof. By contrast, at least since the early 20th century, the Leibnizian ideal has developed into even stricter standards. So let's call them the post-Leibnizian standards of proof. Now, to be clear, I'm using these as ideal types, as Ian Hacking did, for the purpose of organizing discussion. I'm not making a claim about the historical origins of all aspirations to understanding, tracing back to Descartes, or all aspirations to mechanizing proof tracing back to Leibniz. I mean, that would be wildly inaccurate. And as we could see in Jeremy Avogad's talk, even in the 17th century, there were many other ideals, like like those of Isaac Newton or Christian Huygens. Okay, so the Cartesian ideal has been replaced by more realistic standards because it repeatedly faced all kinds of practical challenges. So, for example, some proofs are too long and complex to fit in one's mind all at once. Right? So we end up with a slightly modified version of the ideal as a practical standard, which we might think of as something like this. You know, after some study, one understands the overall strategy of the proof in each of its parts and can get it in one's mind one part at a time. Okay? Now, even then, we run into another challenge. Some proofs are beyond the grasp of an isolated individual, and their construction or verification may require multiple people. So we have discussed many examples of this already. We've discussed accepted proofs, like that of Fermat's last theorem, as well as controversial claimed proofs, like that of the ABC conjecture. And in all of those cases, the controversy boils down to whether the proof would stand a further modification of the standard, which we might call something like this. Each part is understood after some study by some group of trusted specialists. Okay, trusted specialists. Now, what does it mean to be trustworthy, and what does it mean to count as a specialist for this purpose? And the point here is that the adjudication of proofs is ultimately a social process. And so in practice, the adjudication of specialized proofs relies on social mechanisms, such as peer review, specialist journals, committees, awards, degrees, and various symbolic markers of reputation and trust. Now, sociologists like Claude Rosenthal and Christian Greifenhagen and historians like Michael Brani have studied these social mechanisms in the practice of mathematics. Now, how have computers changed these post-Cartesian standards of truth? So one significant change happened with the introduction of computer-assisted proofs by exhaustion. Right, so some proofs require computers to exhaustively check a long list of cases. And the classic example was the proof of the four-color theorem in 1976. But there are many other examples, like the proof of Boolean Pythagorean triples, of the Boolean Pythagorean triples problem in 2016. And in that case, even after narrowing down the list of cases, the proof still involved checking around 1 trillion cases. Right? So in any case, we end up with a modified standard that we might think of as something like this. After some study, one understands the proof's overall strategy, as well as the computer program that checked all the cases. Okay? Now, because this standard is another step away from the Cartesian ideal of total understanding, computer-assisted proofs by exhaustion have tended to generate quite a bit of unease. So these are some of the, just some of the standards of proof focus on understanding, which I'm calling post-Cartesian. Now, what happened to the Leibnizian ideal? And as I've mentioned, it has developed into even stricter standards. So one key transformation was the turn to axiomatic proofs in around the early 20th century. Now this was the turn that was advanced by David Hilbert's axiomatization of geometry at the end of the 19th century, then later embraced by various mathematicians in the first decades of the 20th. The members of Bourbaki are closely associated with the turn to axiomatics, and that story is very much part of the kind of mainstream account of proof that we may find, for example, in undergraduate curricula. So we end up with a standard of proof that we might think of as something like this. Every step can be checked line by line by means of strict logical deductions, and in principle can be traced back to axiomatic foundations. Okay, so the key here is in principle, because in practice, of course, not all published proofs, and actually very few, even after the axiomatic turn, are actually traced to the axioms in any kind of very explicit way. So, and what counts as the proper foundations has continually been the subject of dispute. So until the late 19th century, one prevalent idea was that the foundations of geometry were grounded in observation of physical reality. This idea was challenged after the formulation of non-Euclidean geometry, which raised the question of whether the foundations of geometry should become detached from physical reality. Now, Hilbert's response to this question launched the turn to axiomatics, as historians Alma Steingart and Leo Khoury have explained. And if you're curious, Alma's forthcoming book, titled Axiomatics, also shows how axiomatics influenced broader intellectual transformations, including in social science and even in abstract art in the mid-20th century. In the foundations of logic, there were numerous controversies all over the world, particularly about the law of excluded middle. There were multiple efforts to devise alternative logical foundations, just, for example, in the late Russian Empire, which have been documented by historians Ksenia Tatarchenko, Anya Yermakova, and Lisbeth Demont. And as we've seen in Emily Reel's talk about univariant foundations and homotopy type theory, there are compelling reasons to question our choice of foundations even at present. So disputes over foundations persist. So again, how have computers changed at now the post-Leibnizian standards of proof? So we've been talking a lot about the proposals for formally verifiable proofs, like starting with formal languages like AutoMath in the 1960s and culminating in today's systems like Coq and Lean. And these proposals involve an even stricter post-Leibnizian standard. Okay? We might think of it as something like this. Every step can be checked by a computer program and traced back to the axiomatic foundations encoded in the program. Now, this standard of formally verifiable proofs is not necessarily in conflict with the Cartesian ideal. As Johan Komelin has suggested in his account of the liquid tensor experiment in the first day of talks, a formal verification can sometimes serve to improve one's understanding of a proof in a quasi-Cartesian sense. Okay, now we have to understand how these post-Cartesian and the post-Leibnizian standards come together. So, what is the present relationship between these competing standards of proof? Now, I think that's a very difficult question, and I'm not going to try to claim any sort of conclusive answer, but I'm going to try to offer my tentative approximation. So I'm still not sure of the answer, so let me know if this sounds reasonable or totally off to you, but this is my best approximation at the moment. So post-Leibnizian standards, as in the axiomatic and the formally verifiable proofs, they tend to define how we adjudicate the validity of a proof in principle. Right? So even if a published proof may not include every detail, we consider it valid if we believe that every step would be valid if we checked. However, post-Cartesian standards, so standards of understanding, are still a central part of mathematical practice. And most mathematical results are neither formally verified nor explicitly traced to axiomatic foundations. And in practice, we depend mainly on standards of understanding and social mechanisms, such as peer review, to adjudicate the validity of a proof. So in principle, in practice. Now, post-Cartesian standards also play a role in additional considerations beyond validity. Right? So, for example, a proof is often said to be better or more elegant or more interesting, or to contribute to a deeper understanding when it approximates the Cartesian ideal. So among equally valid proofs, we tend to prefer those which are shorter, which can be understood by many people, and which do not require computers. Okay. Now, we might be tempted to frame these different standards of proof in terms of objectivity and subjectivity. We might see Leibnizian-derived standards as objective and Cartesian-derived standards as subjective. But I would say that this is not quite right. So to begin with, the modern concepts of objectivity and subjectivity are much younger than the Cartesian Leibnizian distinction. Right? So Descartes and Leibniz lived in the 17th century. The distinction between objectivity and subjectivity emerged much later, only in the mid-19th century. As historians of science Lorraine Daston and Peter Gallison write in their book on the history of objectivity, to be objective is to aspire to knowledge that bears no trace of the knower, like knowledge unmarked by prejudice or skill, fantasy or judgment, wishing or striving. Okay? Now, there is certain senses of this that would apply to pretty much all of mathematics, and then there are certain interpretations of this that would apply to almost none, right? So that's one of the reasons why I don't see the objectivity and subjectivity distinction as the key issue at play in these discussions of automation. Now, another reason is that even in post-Cartesian standards, like the elegance of a proof, there may be a strong consensus regarding certain aspects. So a preference for, say, shorter or simpler proofs is not necessarily a marker of subjectivity. And even if one is committed strictly to post-Leibnizian standards like formal verification, one cannot achieve objectivity in certain senses completely. There are many aspects regarding which there is no consensus. For example, the choice of which axiomatic foundations are better for formal verification is the subject of considerable disagreement. So different mathematicians have different preferences. So mathematical knowledge, even then, does bear a trace of the knower in some sense. So in any case, the key issue here, in my view, is not objectivity or subjectivity. I think a more relevant distinction for these discussions of automation is the degree of reliance on explicit versus tacit knowledge. So post-Cartesian standards of proof tend to rely heavily on tacit knowledge, i.e. knowledge which is difficult to formalize or codify explicitly. So how do we know which proofs are better or more elegant or more interesting? How do we develop an intuition or a deep understanding of a proof? How do we know which details to include and which to exclude from a published proof? How do we know whether a published or unpublished claim is trustworthy? Now, these are not things that we learn from explicit or formal instructions. These are things that we learn mainly through practice over time. So in sociological terms, they constitute tacit knowledge. Now, the classic example of tacit knowledge is learning to ride a bicycle. You learn by doing, not through something like a textbook. So it's only through practice over time that we develop what people might call a mathematical intuition or a deep understanding of a topic. It is only through practice that we learn which proofs are better, more elegant, and more interesting, or which details need to be included and which can be excluded in a published proof, or how to assess the trustworthiness of a claim that you cannot check yourself. Now, tacit knowledge also tends to refer to modes of knowledge that which are harder to teach to computers. So it may be tempting to imagine that the ultimate outcome of automation would simply be the elimination of tacit knowledge from mathematics. Okay? So I am not so sure for reasons that I will explain later. But now I want to turn to the question of the future. So what might happen to our standards of proof in a more automated future, as in Accia's hypothetical LF0? So Accia has considered the impact of automation on the evaluation of mathematical results. So he proposes a model of how evaluation in mathematics operates in practice. An open problem is more highly valued if it's considered more difficult and more central. It's difficult if many people try to solve it and fail. It is central if it's linked with many other questions of prior importance. Akshay suggests that automation will change our assessments of both centrality and difficulty, and I agree. But I want to ask about another aspect of the impact of automation on mathematical research. Would LF0 change our present standards of proof? Now, at first glance, it might be tempting to think of LF0 as the ultimate culmination of post-Leibnizian standards of proof, not only in principle, but also in practice, and the death of post-Cartesian standards. Computers would automatically construct and formally verify all proofs, and it would not matter much if humans can understand such computer-generated proofs at all. I am not so sure. It depends on what LF0 does exactly. So let's consider 3 different scenarios of what a system like LF0 might do. They are not mutually exclusive. So the first is LF0 formally verifies existing results. The second is LF0 finds unprecedented proofs which humans can read and understand. And the third is LF0 finds unprecedented proofs which are so long, complicated, or difficult that no human can understand them at all. So in the first scenario, computers formally verify existing results. And if this happens to a large number of results, the gap between Leibnizian principles and practical standards would diminish. We would rely less on social mechanisms like peer review and more on formal verification. So post-Leibnizian standards might adjudicate validity not only in principle, but also increasingly in practice. Now, consider a second scenario in which computers find unprecedented proofs and humans can read and understand those proofs. So this scenario doesn't present a major challenge to our present standards of proof. They could remain roughly unchanged. The proofs would be deemed valid based on post-Leibnizian standards, but Cartesian-derived standards would play a role in other considerations beyond validity. So this is more or less what already happens at present. As long as we trust the computer programs that found and checked a given proof, we would deem the proof valid, as we already do for formally verified proofs. But among equally valid proofs, we would still have our tacit preferences regarding which are better or more elegant or more interesting than others. Now consider a more dramatic scenario. Suppose computer programs are successful at finding new proofs, and some of those proofs are so long, complicated, or difficult that no human can understand them at all, not even their overall strategy. Okay? So in this scenario, what happens to our standards of proof? I don't know. But the answer would depend on our attitude to a potential new standard of proof, which we might think of as something like this. One trusts the computer programs which constructed and checked the proof, even if one may not understand the proof at all. So by not understand the proof at all, I mean not even the proof's overall strategy. So this is different from the case of computer-assisted proofs by exhaustion, where one understands at least the overall strategy. Right? Now, I think this is the key question. Will a standard like this become accepted as sufficient in the future? Only time can tell. And I'm curious to hear what you think. But in any case, I think that one of the reasons why the answer is not obvious or self-evident is that both post-Cartesian and post-Leibnizian standards of proof play a role in mathematics simultaneously. And sometimes they present competing considerations. Many people might not be ready to give up completely on the need to understand a proof in a Cartesian sense, even if they might trust it to be valid in a Leibnizian sense. Now I want to move to a different aspect of the questions raised by Akshay's essay. How might automation change the labor process of mathematical research? So first of all, it's important to note that it's unlikely, at least from a social scientist point of view, that automation will simply replace the labor of mathematicians, leading to some sort of technological unemployment. Akshay already suggested this, and the historical and social scientific scholarship on labor and automation tends to agree. Many scholars, like anthropologist Lily Urani and historian Aram Benanov, have noted that automation doesn't simply replace labor. Right? Instead, automation typically displaces labor. Automation renders some existing kinds of work obsolete, creates some new kinds of work, and changes the perception and value of both the old and the new kinds. Another point is that automation is always partial, right? And automated fear improving is no exception. In the history of automated fear improving, there has always been negotiations about the proper role of human insight and the role of computer assistance, as historian Stephanie Dick and sociologist Donald Mackenzie have noted. So, how might future automation displace the labor of mathematical research? We might begin with a simple distinction of two possible types of work that might exist in the age of LF0. So the first is writing computer programs, which can search for mathematical results, and the other is searching for results using supervised computer programs. Now, which of these modes of labor might become more valuable? I think the answer depends largely on the capabilities of such an LF0. And one relevant question is whether LF0 operates in a mostly unsupervised way, or if it requires substantial human supervision. Perhaps LF0 would be able to search for any results that human mathematicians would deem valuable in a mostly unsupervised way. And in this case, the work of programming it might become highly valued as well. But from the talks by Melanie Mitchell and Jordi Williamson, I have the impression that the unsupervised version is quite unlikely, or at least very far away. More likely, LF0 would require substantial human supervision to search efficiently for proofs that human mathematicians would deem valuable. And in this case, more value might be attributed to the work of using it. Now, it might be tempting to say that one type of work is real mathematical research, and the other is mere computer programming. One is the work of mathematicians proper, and the other is for computer scientists and engineers. But I would resist this temptation. What is interesting here is that, especially in a hypothetical unsupervised scenario, but also in the supervised one, LF0 would blur the boundary between doing mathematical research and doing computer programming, or at least it would treble the boundary. So it would treble the boundary between a type of work previously associated with the discipline of mathematics and another previously associated with computer science and engineering. And this disciplinary boundary is contested, of course, because it structures the institutional organization of universities, the availability of grants, and the perception of prestige. And there is no straightforward way to adjudicate whether a boundary should be dissolved or a new demarcation should emerge. Demarcation is a social process, and it's inflected by relations of power. Social scientists call this boundary work. So this is the work of constructing a boundary, for example, between two kinds of activities or two disciplines, in ways that are useful for the pursuit of professional goals, including the acquisition of intellectual authority, career opportunities, and material resources. Now, there is no intrinsically right boundary between, say, mathematical research and computer programming. Right? The boundary is socially negotiated and renegotiated over time. And indeed, the very birth of computer science as an institutionalized field in the mid-20th century was the product of contested boundary work after a new kind of work blurred the boundary between mathematics and engineering. Now, new scientific and technological advancements, including the LF0 scenario, can blur a previously accepted boundary. And when this happens, the various affected people engage in boundary work and the outcome is uncertain. One possible outcome is the dissolution of the boundary. Another is the renegotiation and reinforcement of the boundary. In the Aleph-0 case, I think it is more likely that the boundary between mathematical research and computer programming will be renegotiated and reinforced rather than dissolved. Because the perception of prestige is at play, there will be much interest in preserving and reinforcing the boundary in some way. So if the boundary is renegotiated and reinforced, what modes of labor might become highly valued and recognized as proper mathematical research? As a consequence of the boundary work, one possible answer might be precisely those kinds of work that cannot be automated. In other words, the kinds of work that computer scientists and programmers cannot do. And one such kind of work already mentioned is the supervised search for results using computer programs. Another is studying and explaining computer-generated results to humans. And another is producing the kinds of mathematical results which computers cannot produce. So automation is almost always partial. It is unlikely that Aleph-0 would be able to produce results of any kind whatsoever. And even if it did, automation would not reach all parts of math uniformly. Right? So some kinds of math will be more automated than others. And at least for some time, we can expect computer programs to be able to produce only certain kinds of results that humans can produce. So in this scenario, if the boundary between mathematical research and computer programming is reinforced, we might expect these modes of labor to become highly valued. Now, notice that these are precisely the modes of labor which tend to rely heavily on tacit knowledge. So one possible consequence of the automation of mathematical research might be an increase in the valuation of tacit knowledge. Now, this is very different, indeed the opposite of the possibility that I had raised earlier, that automation would eliminate tacit knowledge from the research process. So instead of eliminating the need for tacit knowledge in mathematical research, further automation might actually lead to an increase in the valuation of tacit knowledge. We might come to value precisely those things which are harder to teach to computers and which humans learn only through practice. Now, my intention is not to make a prediction, but just to raise one reasonable possibility that looks very different from the popular narrative of technological unemployment. Now, I think it is also worth asking if these possible transformations could have broader social consequences for the mathematical community. And I think it's worth considering that the consequences may not be entirely positive and may intersect with the kinds of social forces that tend to structure labor in general, like class, gender, and race. So let's suppose, for example, that one of the reactions to the prospect of automation of mathematical research is the reinforcement of the boundary between so-called real mathematical research and mere computer programming, and an increase in the valuation of tacit knowledge, often understood as individual insight or brilliance. Now, I want to bring up two cautionary tales that I find helpful for thinking about some possible consequences of this kind of automation of labor. The first cautionary tale is the social scientific finding that fields that place a greater emphasis on perceptions of brilliance tend to have less social diversity, for example, on the basis of gender and race. So in this article from Science in 2015, the authors surveyed people from different fields, asking them to rate their agreement with statements like, being a top scholar of the discipline requires a special aptitude that just can't be taught. So as you see, math and philosophy were the fields in which people agreed the most with such statements. And there are also fields that have relatively low numbers of women and underrepresented racial groups. So there's a correlation, and that's part of this social scientific finding. So I think this is one reason to be careful about how we react to the prospect of automation. If we react by insisting on some notion of tacit human insight or brilliance, we might inadvertently reinforce an idea that sustains social inequalities in the field of math. Now, another helpful cautionary tale is the history of computer programming as a gendered form of labor. So at the beginnings of digital computing technology around the Second World War, many computer programmers were women. And as historians Jennifer Light and Mar Hicks have documented, computer programming used to be considered feminized clerical labor. It was seen as a less intellectually challenging task than, for example, the work of the mathematicians who worked on the theories underlying the machines. Computer programming became a more valued profession only decades later. And as the profession became more highly valued, it also became masculinized, and not just for a coincidence. So the actual character of the work didn't change, but the perception of the work did. In today's mathematical community, it is not uncommon to find the attitude that mathematical research is an intellectually superior activity to something like computer programming. And in debates about the automation of mathematical research, one possible reaction is to try to reinforce the boundary between real mathematical research and mere computer programming. And since this boundary work is reminiscent of the hierarchy of labor in the early history of digital computing, and since the gender gap in mathematical research seems to be larger, even larger than in computer programming, I worry about the possible consequences of such a reaction. Now, I should clarify that I fortunately haven't encountered these kinds of reactions almost at all in the symposium, which is one of the reasons why I've appreciated it so much. But I don't think these kinds of reactions are uncommon in the wider field of math. So I would like to close by noting this possibility. The possibility is that in reacting to the prospect of automation, we might wish to reinforce the boundary between real mathematical research and mere computer programming, as well as to emphasize the value of tacit human insight or so-called brilliance. However, such reactions could be antithetical to the cultivation of a more socially inclusive mathematical community. Thank you very much.